Okay, so today our mathematician spotlight is Emily Riehl. She's an assistant professor at Johns Hopkins University, just a couple hours to our south, and she studies infinite dimensional category theory. And in just a minute, I'm going to let her tell us what that is. But just to introduce the way she's going to talk about it, so in single variable calculus, you studied functions from R to R. So for example, f of x is x squared. So you can think about this as this function takes the real axis and bends it into a parabola. So it bends it into the other R, the image R. And so this function is sort of doing something to this space. So in that way, you can think of a space like R that we start with as a noun, and a function as a verb, something you can do to it. So you think of your space, your R, your domain set, as like a ball, and your function is something you can do to it. You can throw the ball, you can catch the ball, things like that. So that's the idea. So let's listen to Emily tell us about this. So here she is. Good. And here she comes.
Well, actually, I work in infinite dimensional category theory.
Oh, there it is.
And a way to think about what that does is if a category provides a template for a mathematical theory. So there are the mathematical objects, which are like the nouns of the theory, and then there are the transformations between those objects, which are the verbs. But as mathematics becomes more complicated, we need sort of a more robust linguistic template to describe the objects that mathematicians like Rebecca care about. So we might need pronouns, adjectives, adverbs, prepositions, conjunctions, interjunctions, and so on. And so that's where the infinite dimensions come in. We have not only the objects and the transformations, but there might be transformations between transformations, like the homotopy that turns a donut into an infinite dimensional plane and with a hole punctured in it.
If I can add.
All right. So there's infinite dimensional category theory. So now you know. There's just a lot of math out there. We are just scratching the surface here in multivariable calculus, and there is always more math to learn, all the way up to infinite dimensional category theory. So let's see here. I'm just going to start with a bit of a review from single variable calculus. So here's the idea. Today we're going to talk about limits. So I want to remind you about single variable limits. So if you suppose you had some function, so here it is, it's going along, and then there's a hole, and then it keeps going, and then there's a jump, and then it keeps going, but then maybe there's some sort of an asymptote. Okay, so if you're in a middle value here, where the function is nice and continuous, it's easy to deal with. So we usually care about the points where something interesting happens. So let's call these A, B, and C. And then let's look at the limit of this function. Let's call it f of x, as x approaches A, B, and C. So first, how about the limit as x approaches A of f of x? Well, in order for that to exist, the limit as x approaches A from the left of f of x has to equal the limit as x approaches A from the right of f of x. So let's check whether that's the case. So as x approaches A from the left, the function values here are approaching, say, this value. So good. And as x approaches A from the right, the function values are also approaching that same value. Maybe that's 1. So in fact, they are equal. The function values approach the same value as you go to A from the left and the right. So these are equal. And so the limit exists here, and it's equal to 1, or whatever this value is. OK, let's talk about the limit as x approaches B of f of x. Well, again, in order for that to exist, the limit as x approaches B from the left has to be equal to the limit as x approaches B from the right of f of x. So let's check. As you approach B from the left, your function values approach whatever this high value is. And as you approach B from the right, your function values approach, well, whatever this low number is. So they're not equal. There's a jump here. So these two are not equal. So we say this one doesn't exist. And similarly, if we try to take the limit as x approaches C of f of x, well, from the left, the function approaches positive infinity. From the right, it approaches negative infinity. So this one also doesn't exist. So in single variable calculus, in order for a limit to exist, the value has to be the same from every direction of approach. And there are only two, the left and the right. But in multivariable calculus, the limit has to be the same from all possible directions of approach. And since we're in the plane, there are a lot more of those. So that's what we'll be looking at today. Okay, so the first thing to say is that just like over here, there are points where the function is easy, and so we don't have to do anything special. So for example, if we were taking the limit as xy approaches 0, 0 of something like x squared plus y squared, well, let's approach something more interesting, like 1, 2. So the limit as xy approaches 1, 2 of this, well, we can just plug in. So it's 1 squared plus 2 squared is 5. So if the function is a product or sum of functions that are continuous at whatever the point you care about is, a, b, then the limit as xy approaches a, b of f of xy is just f of a, b. Just plug in, just like we did up here. But it gets interesting when the function isn't continuous, and that's what we're going to talk about today. So let's consider the function and the limit in particular as xy approaches 0, 0 of the function x plus y over 2x plus y. So the question is, okay, we have this function which is a surface sitting over the xy plane. And the question is, if you're approaching 0, what is the value of the function going to be? Well, let's try a couple of different directions of approach. So let's try approaching from the east. So this is the line y equals 0, and taking the limit as x approaches 0. And let's also try approaching from the north. So this is the line x equals 0, and we're taking the limit as y goes to 0. So let's try those two. So first, let's approach along y equals 0. So then we would be taking the limit as x approaches 0 of what happens when we plug in 0 for this. So of x plus 0 over 2 times x plus 0. So the zeros go away. This is the limit as x approaches 0 of x over 2x. The x's cancel out. This is the limit as x approaches 0 of 1/2, which is just 1/2. So that tells you if you were on this surface over the y-axis and you were hiking towards the origin, once you got to the origin, you'd have an elevation of 1/2. That's what's going on there. Okay, let's try approaching along x equals 0. So then we're taking the limit as y approaches 0 of whatever this function is when we plug in 0 for x. So 0 plus y over 2 times 0 plus y. So that's the limit as y approaches 0 of y over y. The y's cancel out. So this is the limit as y approaches 0 of 1, which is just 1. So this tells us if we were hiking towards the origin along the above the y-axis, when we got to the origin, we'd have an elevation of 1. So it looks like the limit is different. So here we can say the limit depends on the direction of approach, or rather not the limit, but the value. The value of the function of this quotient depends on the direction of approach, so the limit does not exist. Yeah. Now you might wonder, well, what if I had just gotten the same value for both of these? Maybe I could conclude that the limit does exist. But you can't. Let's try this, actually. So let's see. What is your name? Daniel. Good. Okay. What is your name? Daniel. Good. Oh, great. Okay, so everyone in the room is named Daniel. name learning day is going to be so easy. No? No, right? Because just because we spot check 2 people doesn't mean that everyone is named Daniel. And just because we spot check 2 directions of approach doesn't mean that it's the same for every direction of approach. So that's the idea. Before I go any further, I just want to show you what's actually going on here. So let me pull up this graph. So a nice way to graph this is just by Googling the function. So let me show you that. So if you just type into Google something like z equals quantity x plus y over quantity 2x plus y, you get this really nice graph. So you can see that what's going on here, the reason that things are weird, is because there's something vertical happening along the z-axis. So this red is the x-axis, the green arrow is the y-axis, and then this part in the middle is the z-axis. So you can see that it's sort of, it's got, along the z-axis, the function takes on many values. So that's why if you hike toward it at different levels, you end up hitting the z-axis at different heights. And intrinsically, that's what's going on here. So that is why we get different values for our limit. So I encourage you, as you're working on limit problems like this, to graph using Grapher, which is a native program on the Mac, to use Google, to use a website called Wolfram Alpha, or to use any sort of app. I'm sure you can download a graphing app for your mobile device. There are many that are available.
When you say you're walking in on the x-axis, does that mean you're walking on the surface from that direction?
Yeah, on the surface from that direction. Exactly. Yeah.
So if the limit doesn't exist like we got in this equation, can we assume that the function is continuous or not continuous based on whether the limits exist or doesn't exist?
Yeah, if the limit doesn't exist, then the function is not continuous at that point.
At that point, okay.
Probably because there's some sort of vertical thing going on. Yeah. Yeah. Good. Okay, so let's try this one. So for example, take the limit as xy approaches 0, 0 of xy over x squared plus y squared. So let's try first along y equals 0. So then we would be taking the limit as x approaches 0 of, well, y is 0, so x times 0 over x squared plus 0 squared. So that would be the limit as x approaches 0 of 0 over x squared, which is just the limit as x approaches 0 of 0, which is 0. Okay? So if you walked into this function along the x-axis, you would get 0. Okay. How about along x equals 0? So you can maybe see that since x and y play the same role, exactly the same thing is going to happen. So we take the limit as y approaches 0 of 0 times y over 0 squared plus y squared. So we would get the limit as y approaches 0 of 0 over y squared, which is a limit as y approaches 0 of 0, which is 0. Oh, so they're the same. So maybe the limit exists. Maybe. 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 But let's try along one more direction. So we got 0 2 times. If we were trying to show that the limit doesn't exist, which is the case, we have failed so far in finding 2 different limits. So let's try along the line y equals x squared. Sorry, y equals x. So let's try along the line y equals x. So along y equals x, what happens? So we take the limit as, well, y and x are equal, so we could take the limit as x goes to 0 or the limit as y goes to 0. Doesn't matter. Let's just do x. So the limit as x goes to 0 of x times y, which is x, so x times x, over x squared plus y squared, but y is x, so that's also x squared. So let's simplify. That's the limit as x goes to 0 of x squared over 2x squared. And now we can cancel out our x squareds. So this is the limit as x goes to 0 of 1/2, which is 1/2. So it's so the conclusion is the value depends on the direction of approach, so the limit doesn't exist. So just as if I asked, what is your name? Daniel. What is your name? Daniel. What is your name? So, not Daniel. Oh, shucks. I guess everyone is not named Daniel. Okay, after all. Okay. So, and what does that one look like? Let's just look what it looks like. It's over here. Zoom out. So the idea here is, well, you can see this is the x-axis and this is the y-axis. And the surface actually is along the x-axis and the y-axis. So the value is 0 when you go in. But if we approach along here, above the line y equals x, it's higher. Can you see that? If we approach along this y-axis, it's at this elevation, but up here along the y equals x line, it's like a higher number. So that's why we got 1/2, some higher number than 0. So that's what's going on. Yeah. Okay. So the takeaway message here is that, but. Okay, so you might try 3 different lines, but maybe you want to try all lines at once, because trying a couple of different lines to see if you get something is a bit inefficient. This is actually something that Professor Gomez said in the spiel that I read the other day. He said, suppose someone was studying the line y equals 5x, and someone else was studying the line y equals -x. Well, maybe they could join forces and just study lines of the form y equals mx, and then study everything at once. So that's one trick that we can do. So let's try that for this same example. Okay, and I'll leave this picture up here. So approach along all lines of the form y equals mx. Note that actually this doesn't cover everything, because the y-axis is the line with infinite slope, the line x equals 0, so it doesn't quite cover everything, but it covers everything of this form. So we will get the limit as x approaches 0, doing this one over here, of x times y, which is mx, over x squared plus y squared. Y is mx, so mx squared. So this is the limit as x approaches 0 of m times x squared. Over on the bottom, we can factor out an x squared. We get 1 times x squared plus m squared times x squared. So 1 plus m squared times x squared. And then our x squareds cancel out. So this is the limit as x goes to 0 of m over 1 plus m squared. So the value of this depends on m. We got the same value for our 2 lines, because when x equals 0, let's see, then m is 0. So we get 0 here. And when we're using the y-axis, it's m over m squared, and m squared is much bigger, so this is also 0. Okay, in any case, the point is this value depends on m, so that means the value depends on the direction, so the limit doesn't exist. So if you want to show that the limit doesn't exist, one way is to do this thing with m and show that the limit depends on m. Of course, it may be that you have an easy example where you can just plug in x equals 0 and plug in y equals 0 and get different values. And so actually trying 2 different lines might be an easier way to show that the limit doesn't exist. It sort of depends on the situation. Okay. But you might be thinking, suppose I do all of these lines and the limit comes out the same every time. Now maybe I can conclude that the limit exists. But no. You can't, because it turns out that there are different ways to get somewhere than a line. So if I want to walk this way, if I want to get to the table, I can walk in a straight line. Good way. But I could also walk in some sort of a parabola or something like that, or a spiral. And so we have to actually do all directions of approach. Yeah?
Is it functionally different if you're walking a parabola or a spiral? Because like right at the moment that you're getting to the table, aren't you basically walking in a straight line?
Yeah, basically. Okay, but check out this next surface. So maybe I'll just show you what it looks like before we look at it algebraically. Okay. Ooh, cool surface, right? So this one is carefully designed so that if you approach along any line, you get a limit of 0. But if you approach along the parabola y equals x squared, you get a limit of something else, 1/8 as it turns out. And the idea is, if you're approaching along any line, well, maybe you're just going to be in this nice green flat part the whole time. Or maybe you cross through this carefully constructed high up parabola, but by the time you get to the origin, you're just sort of going straight in along a line. And that if the place where this function is higher is along these two parabolas, and so you really have to approach along the parabola in order to get a different limit than 0. Scary, right? You would not think that it was possible to have a different limit coming along curves than along lines, but it turns out it's true. Okay, so let's try it algebraically to see what happens here. Okay, so consider the limit as xy approaches 0, 0 of the function x to the 4th times y to the 4th over x to the 4th plus y squared cubed. Now that is a contrived function to do some very specific thing, and that is what we're going to make it do. So let's first, this function is constructed so that approaching along all lines of the form y equals mx for m not equal to 0 yields a value of 0, but approaching along the parabola y equals x squared yields a non-zero value. Non-zero value of 1/8 as it turns out. So that's the point of this example. That's where we're going. So let's just see that this happens. So let's approach along y equals mx lines. Then we get the limit as x approaches 0 of x to the 4th times y, which is mx to the 4th, over x to the 4th plus y, which is mx squared, the whole quantity cubed. Okay, I just plugged in. That's all I did. Okay, let's simplify. So this is the limit as x approaches 0 of, let's see, x to the 8th times m to the 4th on the top. And then for the denominator, okay, let's look at this guy. So this bottom thing, this is x to the 4th plus m squared times x squared. So down here I can factor out an x squared times x squared plus m squared. So it's that whole thing cubed. That's what the denominator is. Agree? Okay? And so now over here I can simplify this to x to the 6th times just this quantity, x squared plus m squared cubed. So x squared plus m squared cubed. Okay, now some of my x's cancel out. My x to the 6th cancels out, and 2 of these up here cancel out. I get x squared on the top. So this is the limit as x goes to 0 of x squared times, on the top we have an m to the 4th, and on the bottom we have an x squared plus m squared cubed. Okay, so I'd like to be able to say this thing just goes to 0. Let's see. If m is not 0, then this whole quantity is just some finite number, even if x is 0. So let's just assuming that m is not 0, then we get a limit of 0. Because this thing is finite if m is not 0, and this part is going to 0. So for all of the lines that aren't on the coordinate axes, we get a limit of 0. But let's check out what happens when we approach along a parabola. Okay, so we approached along all the lines of the form y equals mx, with m not equal to 0. So we sort of did all these directions. And what's going to happen next is we're going to approach on the parabola y equals x squared. Okay. So let's approach along y equals x squared. So we get the limit as x goes to 0. Question? Question?
Just talking about if m equals 0 in this case, it would be like if you couldn't determine the limit or evaluate the limit.
Yeah, if m was 0, we'd have a higher, if x was 0 and m was 0, we'd have something of the form 0 over 0. So we'd have to be careful and use a limit to evaluate it.
So this is why I'm guessing we had to approach it from a different, like looking at it through a different curve, because not all the values of m give us a limit that exists.
Well, let's see. So the only things that aren't covered by this form were the axes, x equals 0 and y equals 0. So we could just have, I think if we had treated those separately, if we had done, suppose x equals 0, so on the y-axis, then the numerator would be 0 and the denominator would not, so the limit would be 0. And similarly, if we were along the other axis where y equals 0, the numerator would be 0 and the denominator would be not. So they actually both come out to 0. They just weren't covered by this proof. We have to be careful. This method won't get us there, but the others, the same method as we were doing at the very beginning, will get us there. Okay. So actually the limit is always 0 for lines. Okay, good question. Okay, now let's try along this parabola. So if we go along y equals x squared, on the top we have x to the 4th times y, which is x squared, also to the 4th. And on the bottom we have x to the 4th plus y, which is x squared, squared cubed. Okay, so if we simplify this is the limit as x goes to 0. On the top we have x to the 4th times x to the 8th. So it's x to the 12th. And on the bottom we have, let's see, inside the parentheses, x to the 4th plus x to the 4th. So 2x to the 4th. So 2x to the 4th quantity cubed. And so if we simplify that more, it's the limit as x goes to 0 of x to the 12th over, let's see, 2 cubed is 8. And x to the 4th cubed is x to the 12th. So our x to the 12ths cancel out, and we get the limit as x goes to 0 of 1/8, which is 1/8. So now we know, along these parabolas, these red top parabola parts, the value of the function is 1/8. So if you walked into to 0 along these parabolas, you would get 1/8 as your height. Terrifying. So what is there to do? Gosh, you could try all the lines. Maybe we could carefully construct a function. So if we approach along all parabolas, we would get 0 also. But maybe then approaching along spirals will give us something else. So the thing to do is to convert to polar coordinates for 2 dimensions or spherical for 3 dimensions, because then you can approach from all directions at the same time. So. Okay, so to show that a limit exists, if that's what you want, or as a fast way of showing that limit doesn't exist, maybe, convert to, in 2 dimensions, polar, and take the limit as r goes to 0, and in 3 dimensions, spherical, and take the limit as rho goes to 0. So that's the plan. Okay, so let's do an example. So for example, suppose you want to take the limit as xy goes to 0, 0 of some function like x squared over square root of x squared plus y squared. So we're approaching the origin here, and we want to approach from all the directions. So we'll translate this into a limit as r goes to 0. But now we need to convert to polar. So remember, x in polar coordinates, x is r cos theta, and y is r sine theta. Okay, so that gives us our x. And then x squared plus y squared. Can you say what it would be? R squared, yeah. It's just r squared, because it's the distance to the origin squared. So we can plug these in. X is just r times cosine theta, so that's squared. And in the bottom, we have the square root of r squared. And then we can simplify this. This is the limit as r goes to 0 of r squared times cos squared of theta over the square root of r squared is plus or minus r. But let's take it to be positive. So over r. And now this r cancels out with one of the r's in the numerator. And we get the limit as r goes to 0 of r times cosine squared of theta. Now this r is going to 0. And this cosine squared of theta is bounded. Because cosine itself is between -1 and 1. So cosine squared is also between -1 and 1. So this is bounded. So since we have something going to 0 times something bounded, we get 0. And that shows that the limit really is 0. We approached from all directions at the same time. Because as our r was going to 0, even if our theta was doing something crazy, maybe our theta is making us spiral around. Maybe our theta is making us come in on a parabola. This covers all of it at the same time. It says, I don't care what theta is doing. The limit is always 0. Yeah?
So, to make our lives easier, we convert it to polar or spherical coordinates. But what I'm trying to understand is, what can this system tell us about our function that we don't already know from lines, since circles are like infinite lines in different angles, if that makes sense?
It does so that what this does more than what lines do is approaches in all ways at the same time. So it covers, yeah, once in just one limit we can do all the ways, all possible ways of approaching the origin. Whereas with lines, the only way you're doing is approaching in a straight line, which is not all the ways.
I see.
Yeah.
I mean, I think I get it. It's just that with the like the Cartesian system that we were using before, it's just harder to do every infinite gradation. Is that the difference? Because, like, I guess in my head, I'm thinking that we are just going through all the degrees in the circle when we're using
A line?
a
polar
system. We're just going through all, and I don't know. I think I'm thinking the same way you are in terms of thinking we're just scanning along all of that, and how is that like conceptually different than doing the same thing
with lines? With
in the Cartesian system?
yeah, well, so the idea would be that even if you're going to eventually, for example, approach the origin along the x-axis, lines only cover coming straight in from the x-axis, not coming in on a parabola, not coming in on some sort of other kind of a curve, which are other ways to come in at a 0-degree angle. Yeah, and polar does that. Okay, so this is the way to show that the limit exists. It can also pop out that the limit doesn't exist if you get something that depends on theta. So for example, let's do one in spherical coordinates. So take the limit as x, y, z approaches 0, 0, 0 of x times z over x squared plus y squared plus z squared. And now we want to convert this to a limit as rho goes to 0 of something in spherical coordinates. That's the goal. So let's just write down the conversion. So in spherical coordinates, I always only remember what z is. So I know that z is rho times cosine of phi. And that makes these rho times sine of phi, rho times sine of phi. And this is r. And then x is r times cos theta, and y is r times sine theta. Okay, so now, and then similarly, let's see, x squared plus y squared plus z squared. Can you say what that is in spherical coordinates? Rho squared, exactly. It's, again, just the distance of the origin squared. So let's plug in for this. So x is this big thing, rho sine phi cos theta. Z is rho cos phi. And then x squared plus y squared plus z squared is rho squared. So if we simplify this out, we get the limit as rho goes to 0. Let's pull out the rho squared times some angle stuff. So times sine phi cos theta cos phi over rho squared. So our rho squareds cancel out, and we get the limit as rho goes to 0 of sine phi cos theta cos phi. And there's no rho's in here, so this is just sine phi cos theta cos phi. So here the limit, the value depends on the direction, so the limit doesn't exist. Yeah, because it depends on how you come in with your angles. Yeah. Yeah, questions or ideas? Okay, and generally if you end up with something in terms of angles, you can just say the limit, the value depends on the direction. You don't have to necessarily plug in some angles and show it comes out differently. The only thing to be concerned about is if you got something like cos squared theta plus sine squared theta as your limit. That looks like it depends on theta, but it's actually always the same. Yeah?
What are some telltale signs that, make us use one coordinate system over the other, or just stick the Cartesian plane?
So the telltale thing you want to see is, does the limit exist or not? Because if the limit doesn't exist, you'll just try some lines maybe. And if the limit does exist, you'll want to convert to a different coordinate system. And the telltale sign that a limit doesn't exist is that the total degree on the top is equal to the total degree on the bottom. So you have like x times y on the top and x squared plus y squared on the bottom. They both have total degree 2. When you have different total degrees, like maybe power 1 on the top and power 2 on the bottom or something like that, the limit tends to exist. But you have some examples to try for your homework where you'll figure this out. Yeah. Question? No. Yeah.
Would you recommend doing everything in polar and spherical coordinates, or would you recommend trying to
So converting to polar and spherical is like a huge sledgehammer. It will always work. You can always hit things with it. But it may be that sometimes a smaller thing is useful. Like if you can just plug in x equals 0 and y equals 0 and get 2 different limits and be done, that's probably easier. You can always use the sledgehammer, but you may find that other things are easier in other places. Okay, thanks guys. See you next time. All right, that's good. Okay.